3.6 is optimization, and we've really kind of already done the main idea behind optimization when we did the EVT. What did we do in the EVT? Or what did the EVT say? Absolute extrema, right, which I knew what you meant when you just said extrema, right? So did everyone else, because if you don't say absolute or global, it means extrema. Yeah, so the EVT, remember, said if the function is continuous on a closed interval, you're guaranteed to have both a max and a min on an interval, okay? So when you have max and min, you can kind of think of the max as being the biggest y value and the min being the smallest y value. And anytime you use the superlative case, like the biggest, the smallest, the most ugly, or the ugliest, I guess, would be that word that way. Yeah, the most, not the most ugliest, right? Unless you're being poetic. It has to be pretty ugly to do that. Anytime you use the superlative case, you're kind of hinting at optimization. Because what does the word optimize kind of imply in the real world outside of a math class? Most efficient. Yeah, it has something to do with efficiency, right? And efficiency kind of means that there's certain parameters within which you must work, and you're trying to get the best outcome per set of some kind of limiting factor or set of parameters. And that's what optimization is in math. We're trying to be the most efficient. We're trying to find the biggest or the smallest quantity in a certain closed system within a certain set of parameters, okay? So really what we're looking for is absolute extrema, much like we did for the EVT. If we have a closed interval, it is an EVT question. If we don't have a closed interval, we're going to have to learn to justify it some other way. But the cool thing about this section is you're not going to be necessarily handed an equation and said, here, find the absolute max and absolute min. You're going to be given a scenario, a word problem, oh boy, and you're going to actually have to write your own equations. So that's the part of the optimization that some people take aversion to, having to write your own equations. I like writing my own equations because then I know they're mine. They're not used. Someone else didn't use them already. They're fresh. I made them, and I'm proud of them, right? So hopefully you take the same attitude. All right, here's an example. Before Facebook or Xbox or whatever y'all use, Atari, I don't know what the latest system is. The ancient boys in ancient Greece and even in other parts of the world didn't have all the distractions that we have today. So they used to like challenge each other to contests such as this on example 1. Find two positive numbers whose sum is 60 and whose product of one times the square of the other one is a maximum. And they'd say, okay, your mark said go. And the boys in their togas would be writing in the sand, trying to figure out what the answers are. And the first person to come up with the right answer won, like, I don't know, a free toga sash or something, whatever. Or a free leaf for their hair or something. I'm not sure. I wasn't there. We're going to do that, but we're not going to do by the guess and check method. Because the guess and check method doesn't guarantee that you're finding the optimal quantities. All right? So let's go ahead and set out and see why this is optimization. Find two positive numbers. So what type of numbers are they talking about? Positive. Good. Real numbers or just integers or what? If it doesn't say, what do you assume? No, you assume real numbers. So find two real positive numbers that add up to 60. Oh, that's easy. That's easy, right? 16 and 14. Did I win? 1 and 59. Did I win? Well, there's a lot of numbers that add up to 60. So here's the constraint, right? Not so fast. Whose product of one of them times the square of the other one is as big as possible. Don't get your toga in a knot, okay? So when you're reading this, how do you know that it's an optimization question? You're trying to find the maximum something with a given parameter. The parameter is they have to add up to 60. So the first thing you're going to do is figure out what quantity it is you're trying to optimize, in this case maximize. We're trying to maximize the what? Well, let's go back and read. We want the product of one times the square of the other to be as big as possible. So we're trying to maximize the product. All right, so that makes it optimization, the absolute maximum product. Now we got to write our own equations. So I would encourage you to start with the quantity that you're optimizing, okay? So let's call the product some letter. A for product, H for product, P for product. Choose your own letter. I'm going to choose P for product. Remember, you're writing your own equation, so you get to choose whatever variable you want. I like P for product. If I put M for multiplication, that's not that bad. But if I put A, I might be thinking it's for addition or aardvark function. So I'm trying to make it meaningful. So the product of one number times the square of the other. So I got two numbers. What do you want to call the two numbers? A and B, X and Y? Yeah, let's call it X and Y. So the product of one times the square of the other. That's going to be X times Y squared. Or X squared times Y. It doesn't matter. At this point, you're committed to letting Y be the other one that's being squared. Okay? So P equals XY squared. That's it. That's the equation that we're trying to find the absolute max value of. Now, what's wrong with that? Yeah, it's in terms of two variables. We can't work with it right now because we don't know multivariable calculus. We have to make P either a function of X or a function of Y. And of course, we need to involve the constraint, because otherwise, someone might just say, let X be like 100 million thousand and let Y equal like 100 million thousand times 2 squared. Those aren't going to be numbers that work, because what's the constraint? They got to add up to 60. Oops, okay, I forgot about that. So that's the constraint. You're trying to find the biggest product with the condition, and I'm going to go ahead and call this the constraint equation, the fact that the two numbers have to add up to 60. So really, you're going to write two equations, and it doesn't really matter the order in which you write them. The constraint equation is X plus Y equals 60. The function you're trying to maximize is P equals XY squared. So once you have both of those equations down, it turns into an algebra 2 problem. You're going to do substitution. You're going to use the constraint equation to solve for either variable, and then you're going to plug that into your primary equation to get it in terms of a single variable. And it doesn't matter which one. So kind of play it smart. Make it easy on yourself. It's just as easy to solve this for X or Y, correct? But what you're doing with it, well, if you solve for X, you just plug it in. If you're solving for Y, you're going to have to plug in and then, square it. That's a lot more work, right? A lot more fun, possibly. So you do it that way, and I'll do it the boring way, and we'll see if we get the same answer. We should, right? Because ultimately it doesn't matter. So in the interest of, not having, a level of fun that's practically illegal, I'll solve for X, okay? And now I'm going to plug that in right there. So P is going to equal X, which is now 60 minus Y times Y squared. Hooray, hooray! You've gotten your primary equation that you're trying to maximize in terms of a single variable. Okay, so next, what you want to do is maybe take the derivative of it. Let's simplify first. Most people screw up the product rule, so let's go ahead and not use the product rule. Let's distribute 60y squared minus y cubed. If you want, you can also say not just P, you could say it's P of Y. If you want. It is a function of Y. I don't think I'm going to do that. I'm just going to leave it as P for product. Okay, now here's kind of an important part. This is a cubic polynomial. What's the domain of a cubic polynomial? All real numbers. We're not allowed to use all real numbers here because we have a mathematical model that represents a real life situation. So we need to come up with a relevant domain. If Y is one of the numbers, what do we know Y has to be? It has to be positive. So we know Y has to be greater than 0. There's probably an upper bound on Y as well, right? But that's not as critical right now as saying, okay, it can't be a negative number. Okay, so we know that Y has to be a positive number. Let's see if that's good enough. So now to find the maximum, we need to see where we have critical values. So let's do that. We need to find the critical values. So P prime is equal to 120 Y minus 3y squared. Is that ever undefined? No. Is it ever 0? Maybe so. Let's see. We'll set it equal to 0. And now we'll factor it by pulling out a 3y. Yeah, I like that. That gives you a 40 minus y. And you get the following two numbers, y equals 0 or y equals 40. Do both of those make sense in the context of this problem? No. Good thing we already thought about a relevant domain. Y has to be a positive number. So 0 is not in the domain. It is a critical value of that polynomial, indubitably, but it is not a value in our relevant domain. So we only got one critical value out. Does that mean it has to be the answer? 99 times out of 100, if you get one output and you have no endpoints, we don't have endpoints here, right? It's going to be probably the answer. But we need to verify. What if y equals 40 is the value that minimizes the product instead of maximizes it? That'd be embarrassing, right? Ooh, we found the wrong one. So how can we tell if that's going to give you a max or a min? Plug in values on either side. How about a little number line chart? Does that work? Yeah. So let's do that. We'll have y and p prime now. And remember, our relevant domain is everything greater than 0. So I'll put like a little parenthesis here and a 0. So here's 40. And pick a number to the left of 40, but not negative. 20? I like 1. You do 20, see if we get the same thing. A number to the right of 40, I'll make up for it now. I'll put 4,000. Okay? There we go. Now, we're going to plug it into the full-fledged factored version of f prime or p prime. If you plug in a 1, you get a positive times a positive, which is positive. If you plug in a 4,000, you get positive times negative, which is negative. Now, are there any other critical values for this function ever again? No. So notice this tells us by the first derivative test that we have a local max at 40, right? But in the context of our relevant domain, we can also say that this is the absolute max on our relevant interval, okay? Because the only other place it might change signs is to the left of 0, which we're not allowed to do. So on the interval from, we'll do it this way, y equals 0 to infinity, we know that, and here would be the justification. Let me go ahead and write it out. This is kind of the most undesirable part, the justification when we don't have endpoints. So you'd say since p prime is greater than 0 for y between 0 and 40, and p prime is less than 0 for all y to the right of 40, like from 40 to infinity. That's a true statement. Y equals 40 maximizes, and if you want to put in parentheses here, absolutely, it maximizes absolutely the product. That's another way of saying it's the absolute max. So that's the difference between a local argument and a global argument. For optimization, we want global extremas, all right? So if you just said at or p prime changed from positive to negative at 40, that's a local argument. When you basically say that p prime is positive everywhere to the left on our relevant interval, and p prime is negative everywhere to the right on our relevant interval, that gives it the global feel, okay? If you want to even add the word all right there to emphasize the global feel, that's fine. It's automatically a global argument when you include all the values in the relevant domain, okay? So that means basically that on our relevant domain, it's going to be going up until 40, and it's going down forevermore afterwards. And so it's not just a local max, it's an absolute max. Okay, so now that we know it's an absolute max, and by the way, you're not going to have to do justifying all the time. But now that we know that 40 is the value that maximizes the product, the last thing you do is probably the most important thing. You want to answer the question. I know that seems kind of like a no-brainer, but there are a lot of things related to the 40 that they could have asked. Did they ask for the two numbers, or did they ask for the actual product? Well, let's see. It says find two numbers. All right. So now I'm going to list the numbers. It does matter which one I'm calling y and which one I'm calling x, because remember, one of them was being squared and the other one wasn't. So here's how you're going to answer the question. The two numbers are y equals 40 and x equals 20. There you go. There's a couple of ways to find. Well, the easiest way is to plug it back into that original equation that you saw for the other variable, to make it in terms of a single variable. That one's ready to go now to find the other variable. So if you plug 40 in there, 60 minus 40 is 20. If you just said the two numbers were 40 and 20, that wouldn't cut it. Because when you tell me the two numbers are 40 and 20, I don't know which one of those we're supposed to be squaring. But by listing it as xy squared, and then listing them as x and y, we've got it. So now we know indubitably that there are no other numbers that are going to give you a larger product that add up to 60 than these two guys right here. Okay, we found the absolute max. So that's optimization in a recreational kind of way, right? Now remember, if you do trial and error, just because you go through a whole gamut of things that add up to 60 and you pick the one that had the largest product out of your list, that doesn't make it the largest product out there, right? That's why this is so nice. It finds them absolutely, indubitably. Okay, so there was basically your optimization question. That idea is going to be used in every other type of problem. Yeah?
So if you set your domain of y and, for that matter, x to be somewhere between 0 and 60 at the beginning?
Yeah, that works too.
Would that be okay?
Yeah, you know, yeah. First of all, we're calling the domain for our variable. It's y. Y is usually the range, right? You're going to assign variables to be anything you want. So once you get a function p as a function of y, y becomes your independent variable, regardless of what letter you used. And so that's why we're calling it the domain. We just came up with a lower bound, but really you could come up with an upper bound, right? Just like you said. You actually know that y has to be between 0 and 60. Okay? Because if it was 60, then the other value would have to be 0 or negative if it was bigger, and they both had to be positive. So if you can get a smaller relevant domain, that's not a bad idea. But in this case, notice everywhere to the right of 40, our p prime was negative. Now, if I thought that for an instance there was another critical value, I would want to make sure that then I'm putting an upper bound of 60. Because if that sign then changes after 60, we can't say the same thing then. We can't say it's negative everywhere to the right of 40. But in this case, it wasn't. So the tighter you can get that relevant domain, the better off you're going to be. All right? But the point, though, in this case, is the EVT doesn't apply, does it? The EVT doesn't apply because we don't have endpoints. These are not greater than or equal to or less than or equal to. If it were two endpoints, we could actually justify by using the game show, the EVT method, the closed interval method. But in this case, we had to do a modified first derivative argument. All right, moving on. Let's try it on another one. Example 2. An 8-inch long pipe cleaner used to clean pipes, believe it or not, and to form rectangles for a calculus class. That's another good use of pipe cleaners. It's bent into the shape of a rectangle. What dimensions of the rectangle will produce the rectangle with a maximum area? So reading it, what's the giveaway that it's optimization? Maximum area. And there is a constraint, right? We're limited by what? The length of the pipe cleaner. All right? If the length of the pipe cleaner was anything you wanted it to be, you could find an area to be bigger than the world if you can find a pipe cleaner big enough. But ours are only the 8-inch long pipe cleaners. Okay. Here's another use of a pipe cleaner, making it into a calculus ninja. Yeah. Okay, cool. This is one now, unlike on number 1, where it's a geometric problem. And for geometric problems, you might want to draw a picture. A relevant picture, not like a seascape or something. Draw a rectangle. All right? Now, the rectangle has two sides. I don't know what they are. You want to call them X and Y? L and W, A and B, Omicron and Lambda. I don't care. Whatever you want. X and Y. That looks good. All right, so let's go ahead then and stick to the flow chart. We drew the picture. That was the first. We didn't draw the picture of the numbers on number one. It wasn't geometric. Let's write an equation for what it is we're trying to maximize. We're trying to maximize the area of this here rectangle, which now have side lengths of X and Y. So I'm going to use A for area, regardless of what you recommend. And based on my variables, it is XY, right? The area is X times Y. So there's your primary equation. That's the one you want to maximize. But it's two variables. We need to write the area as a function of X or Y. So now, what's the constraint? Very good. The perimeter of this rectangle has to be what? 8. Bless you. The perimeter has to be 8. Perimeter has to equal 8. And based upon your variables, or my variables, that's 2x plus 2y has to equal 8. So there's your constraint equation. That's the one that you're going to be using to get your primary equation in terms of x or y. Now you might notice that you could divide out 2's all the way across, right? That means x plus y has to equal 4. Solving for x or y is just as easy, one way or the other. And plugging in over here is just as easy. So since we solved for x last time, let's just give y a turn to solve for him. So y is equal to 4 minus x. I'm going to box that equation, not because it's my final answer and I'm walking away, but because I might need to come back to that dude. So he's going to stand out a little bit more if he's in a box. Can't go anywhere either because he's in a box. So we plug it in over there, and we get the area then is going to be x, which is x, times y, which is now 4 minus x. Congratulations, you got your equation now in terms of a single variable. That's what we want. So now, since we're going to be taking the derivative and finding critical values, let's go ahead and distribute. And now we come up with a relevant domain. What do we know about x? Can x be negative? No. Can x be 0? No. X has to be some positive number. And sure, you could give yourself an upper bound, right, if you want. You could say that x is going to be between 0 and 8. 8 would be good. Can you even do better than 8? You could actually say 4 and still be safe, right? Because if x is one side, if you laid the pipe cleaner out and then bent it in half so that y was essentially 0, it's going to come back the other way. You got 4 going out, 4 coming back. You know that's not going to be the answer because it's a geometric shape. And with that, it would have 0 area. That would minimize your area to 0, yeah. So 0 to 4 is good, or if you just want to say x has got to be positive. It doesn't really matter so long as you think about a relevant domain. Now we'll find the derivative. A prime equals 4 minus 2x. It's never undefined. And by the way, we're interested in the values where the derivative is 0. We want our function that is the derivative to be continuous. So we're going to be looking for the nice critical values, the Rolle's theorem critical values. So that gives you x equals 2. That's the only critical value we have. We don't have endpoints. In that case, when you don't have endpoints and you only get one critical value, most of the time that's going to be the optimal value that you want. If you didn't have to justify, you could kind of roll with it. But let's think about the justification. You can't use the closed interval argument again. You can't find the area at 0, find the area at 4, and then find the area at 2 because the endpoints don't make sense. So we could do like another modified first derivative test. But think about what the graph of area looks like. This is probably an easier way. That's the graph of a parabola, right? That opens down. And don't we know that the vertex location is going to be the location of the absolute max because it opens down? Yeah. So we know that for a fact. Now, if you want to justify it, you can almost do a second derivative modification. The second derivative is negative 2, which is less than 0 for all x in your relevant domain greater than 0, right? When you say the for all, you're making it a global argument. You're basically saying this graph is concave down everywhere, and therefore it's not just a local max, it's an absolute max by a modified second derivative test. Okay, the point being we have our optimal value. It's x equals 2. So the last thing we do is we answer the question. Did it want both side lengths or did it want the area? I don't know. What does it say? What dimensions? Okay, so x is 2, and I just need to find y. How do we find y? Plug it back in there. 4 minus 2 is 2. Hey, those are the same. So the optimal rectangle is a 2-inch by 2-inch square, as it turned out. But I'm answering the question. The optimal rectangle is a 2-inch by 2-inch. We don't need to put x and y there this time. Why? Because they're the same. Yeah, because they're the same. And they are just dimensions one of a rectangle. One could be one side and the other could be the other. We weren't doing something different with one of them, like squaring it this time. So is that surprising that the most optimal rectangle is a square? No, not if you know how Mother Nature works, right? Mother Nature likes symmetry. Mother Nature likes the law of entropy to expand out and to become stable. And a square is the most optimal rectangle. It's the most efficient rectangle. It's very stable as well. So yeah, shouldn't be surprising. All right, so there you go. We've got 2 under our belt. That's where we keep all the problems that we finish working, right there under the belt. Ready for another one? What time do we get out of here on this Wednesday? I forget. 55. Okay, cool. We got enough time for the next one. Example 3. Low resolution ladybugs. A ladybug farmer. A farmer of ladybugs, right? Someone last year said that would be a rancher, a ladybug rancher. God, you're a wet blanket. Come on, man. A ladybug farmer has 500 inches of fencing. Ladybugs are small. And wants to fence off a rectangular field that borders along a straight river to enclose his grazing ladybugs. He needs no fence along the river because ladybugs can't swim. And he has also clipped their wings. So a very delicate process. They're not going to fly over this fence. Okay? What are the dimensions of the field that he has to fence off that will provide the largest grazing area for his hungry ladybugs? Okay, let's draw a picture. This is one where it's a geometric problem. Here's the river. We want to make a rectangular pen for the ladybugs. We have 3 sides now instead of 4 because we don't need a fence along the river. Assume always no waste on this either, okay? You're going to take the fencing and just turn the corner and then stake it in ground. You'll never have any waste on these problems. These are the optimal conditions, all right? So what do you want to call the side lengths here? I'm going to go with something different now. I'll call it A and B. Crazy, I know. You want to stick to X and Y, that's fine. L and W, I get it. We're trying to then what? Maximize or minimize something? Maximize. So let's write the equation of what it is we're trying to maximize. They're going to have the most area to graze when the area is the maximum. So I'll use capital A for area and little a for a side length. Oh, I'm already seeing a possible conflict. I'm using 2-letter A's. Is that okay? One's capital, one's lower. That's fine. Okay, cool. As long as you know that. So there's the primary equation. Now, what's the constraint? He's got 500 linear inches of fencing, and he doesn't want to have to go to the ladybug store and buy more. So that's going to correspond to the what of the rectangle? The fencing, yeah. It's not quite the perimeter because it's not along the river. But 500 has to be consisting of 2B's and 1A, right? 2B, B plus A. Yeah. So that one is easier to solve for A. That's your constraint equation. I'm going to solve that one for A. So I get 500 minus 2B. I'm going to box that dude. But right now I'm using it to get my area in terms of a single variable. So the area of that rectangular pen is going to be 500 minus 2B times 1B. and you have your area now as a function of b. If you distribute, you get 500b minus 2b squared. And the value for b then, the relevant domain, b is a length, so once again it can't be 0. It has to be greater than 0. Now we'll take the derivative. A prime is 500 minus 4b. Set it equal to 0, and you get 4b equals 500, which means b equals a fourth of 500, which is 125 inches. Now that's the only critical value we got. The endpoints don't make sense, right? Because if you let a or b equal 0, you've collapsed the entire structure down to nothing. So just like before, if you get a critical value, the endpoints don't make sense. Most of the time that's going to be the answer. But in this case, we don't even have to just keep our fingers crossed. Notice the area formula, again, is a downward opening parabola. So we know that the horizontal tangent, where the vertex is the location of the absolute max. So that is the value that optimizes it. Now, to answer the question, did we need to provide the area of the field or the dimensions of the field? What are the dimensions? Does it matter which one I'm calling A and B now? It does, because B is the one that's perpendicular to the river and A is the one that's parallel. So, we'll say the optimal dimensions are, and then we'll list the first one, B equals 125, and A is equal to, you could probably just figure it out in your head. If you plug 125 back in up here, remember I boxed it, made it easy to find. It's going to be, what, 250? 250 inches. So, kind of interesting. We come off the river 125 feet, and we run along the river 250 feet. Is that a square? Oh, okay. So it's not a square. It's not a square. It's actually twice as long as it is deep off the river. But your point is you're using half of the fencing for the perpendicular and half of it for the run. Is that what you're saying? Okay. Yeah, that's correct. So yeah, there you go. It's twice as long as it is wide. And there you go. So now you can give those dimensions to that ladybug farmer. He'll go out there with this little like ruler, and measure, because ladybugs aren't that big. And he'll sleep well at night knowing that his ladybugs ain't getting away because he clipped their wings, and that he's not cruel to them because he's giving them the most grazing area allowable.